Hello and welcome again. So this is lecture number 3, okay, in our electrodynamics course. So last time we used Maxwell's first equation, okay, which was divergence of electric field equals to rho over epsilon naught plus electric field equals to negative gradient of potential. So we used these two equations to derive the most sophisticated equation in whole of electrostats, that is Poisson's equation. Del square V equals to minus rho over epsilon naught. Okay. So basically, whole of electrostatics is to solve this equation. Okay, Poisson's equation. Okay, so because if we know, suppose rho, if we know the charge distribution in a given space, then we can easily find V using this equation. And if we know V, then using this equation, we can find the electric fields in our space. Okay, so basically, this is the main equation for electrostatics. Okay, and we'll learn later on that we can guess solutions. Okay, so we can guess some solutions can guess some solutions for this equation, and that guessing is basically called the method of images. Okay, method of images. So that will come later on. Now let's look at this equation. Okay, first of all, so del square v equals to rho over epsilon. So del square v equals to rho over epsilon naught. So first of all, this equation tells us that the second derivative is related to the local charge density. Okay, remember this is a local equation. So local equation, that means the second derivative of potential second derivative of potential is is related to related to the local charge density. Okay, local charge density. Okay, now let's look at the trivial case and the trivial solution. So trivial case will be when charge in whole space equals to 0. If charge in whole space equals to 0, then the trivial Poisson's equation will be del square v equals to 0. Okay, so this will be the Poisson's equation in that case. Now, what will be the solution for this equation? The solution is simple. We can write a simple solution as v equals to v naught, where v naught is some constant. Okay, so this constant function can easily satisfy this Poisson's equation. Okay, but in general, we'll have some boundary conditions. So this is not easily solvable when we have some boundary conditions. Suppose you have some uh, s- um, you have some metallic sheets with some charges, okay, or you have some conducting spheres with some charges, then this equation has to be solved differently. Okay, now let's take a very simple case. Now first of all, you must understand that in this equation it's easy to go from potential to charge. Okay, if you know potential in the space, you can easily get your charge density, local charge density, but to get potential from local charge density is a little bit trickier. Now, first of all, let's look at the simple potential to V. If you know potential, how to get rho. Okay, so let's suppose that I have some function V equals to A plus Bx square Y. Okay, then what will be my rho in this space? So suppose it's a two-dimensional space. Okay, xy space where potential is given like this. Okay, and I want to find my charge density in this xy plane. So charge density in this xy plane can be written as using our equation, Poisson's equation, del square V times epsilon naught. So epsilon times del square V with a minus sign. Right? Now what about del square V? Del square is a Laplacian operator. So the Laplacian operator, and in two dimensions, Laplacian operator. So let me write it here. So Laplacian operator in two dimensions can be simply written as dou square by dou x square plus dou square by dou y square plus dou square by dou z square. So this is the Laplacian in Cartesian coordinates. Okay. So if I apply this Laplacian operator to my potential function, what will I get? So I will get simply rho equals to minus epsilon naught. When I do differentiation twice with respect to x, first of all, so I'll get 2 dy. Okay, so I'm doing differentiation first with respect to x for this potential function. So this is what I get. Plus, when I do differentiation with respect to y for this function twice, so I will get 0, and there is no z variable, so I'll get This is what I get. So rho equals to minus 2 b epsilon naught y. So this is my charge density in this xy plane. Okay.